Hey, good morning. Today is July 9th, 2024. Today we're going to be talking about capacitor. So what is the capacitor? Basically, if you put two conductors next to each other, and then those two connectors they are a distance d apart, but they do not connect each other. Technically, they form a capacitor. What is the function of the capacitor? Basically, if I dump some positive charge Q in the top conductor, and then the bottom connector will create exactly same amount of negative Q. Okay, so when we say a capacitor have a charge Q on it, that means either the one of the plate have the charge Q, positive Q, or we'll refer to the another conducting material which have negative charge of Q. So the absolute value of those are the same, and then that's what we're talking about when we say the capacitor have a charge Q. On the other hand, the C, which is the capacitance, that is equal to Q over V, where the Q, we already talked about it, but the V is the voltage that apply on top of it. I mean, this is the V. Okay. And then as we increase the charge, for instance, instead of Q, we had 2Q. And then the voltage of V is also 2V as well. So those two cancel are still equal to C, the same C. In other words, the capacitance is not going to change because those relationship is going to be automatically matched. If you have less V, and then the Q will be less automatically. Only under one condition is the V is not large enough. Why? If V is large enough, then they create a very strong electric field in between them, and then they will eventually penetrate through whatever the thing in the middle, either air or some dielectric material. Then the capacitor is not functioning as the capacitor at all. It probably acts as a short circuit or something else. So again, when we set the C equal to Q over V, we say they are under the normal conditions, which V is not large enough. Okay. And then the capacitance, if we're looking at the geometric shape of the capacitor, let's say the capacitor is formed as two parallel plates which are distance d apart. The area of the top plate and the area of the bottom plate, they are the exactly same area. The area is A. So if that is the case, the capacitance is equal to epsilon 0 A over D. A is the area, and then D is the distance, and then epsilon 0 is the electrical constant. That value equal to this guy right here is 8.85 times 10 to the negative 12 over n. No, I'm sorry. This is just I'm sorry. This is the F over n. Okay. So we can check the units, right? So the unit of epsilon 0 is F over m. The unit of A is meter square. The SI unit for the D is meters. So those 2m, m square, cancel with this m square. So the final unit will be F. This is the unit for the capacitance, and that's pretty large if we're talking about 1 F, 1 farad. Typically, in our daily life, we use micro F or nano F. Okay, those are two different units. So micro means 10 to the negative 6, and the nano means 10 to the negative 9. Okay, so those two are very important formulas. And then let's working on a specific problem. For instance, if we have a capacitor like that, and this is A, this is distance T. The A, let's say that's equal to 1 meter square, and then D equal to 1 millimeters. So what would be the capacitance of this specific capacitor? So the C again equal to epsilon 0 A over D, which is 8.85 times 10 to the negative 12 F over M. And then times A, which is 1 meter square, D is 1 millimeter, and then we know 1 meter is equivalent to 1,000 millimeter. In that case, millimeter, millimeter cancel out, meter cancel out 1, another meter cancel out with this guy. So the final result will be this number times 1,000, right? Because when you divide a fraction, you times the reciprocal of that, which is 1,000. So the final result will be 8.85 times 10 to the negative 12 times 1,000 farad. Simplify a little bit. 1,000 equivalent to 10 to the power of 3. So that would be 8.85 times 10 to the negative 12 plus 3. So that would be 8.85 times 10 to the negative 9 farad. And then as we just discussed, this is going to be, this is going to be 8.85 nanofarad. Okay. So the next thing we can ask for is Q. We can ask for how many charge the one of the plate, either one of the plate, to accumulate it if we apply a voltage of a kilovolt. Okay, in other words, V equal to 1 kilovolt. We ask for Q. So Q, again, based on this equation right here, that would equal to C times V. Times V, that would be, what is our C? this right here is 8.85 nanofarad times V is 1 kilowatt. 1 kilowatt. Again, we're going to 8.85 times 10 to the negative 9 farad times 10 to the 3 volt. And then that would be 8.85 times 10 to the negative 6, because negative 9 plus 3 is going to be negative 6. Again, the unit for this guy right here, that actually is the coulomb, I mean the SI unit. So that would be C. And then that would be 8.85, because it's 10 to the 6, negative 6, that's micro. So it's micro coulomb. Okay. So the next thing we can ask for is the electrical field. Since this is a positive charge, this is a negative charge, so there's the electrical field in between those two plates. And then based on the discussion from the previous lecture, that E actually equal to absolute sigma over epsilon 0, where the sigma right here, this is the charge density, right? So again, if you forgot this equations, you need to review the previous slides. So again, since this is the charge density, that basically means that's the charge of the cube over the area, right? So that's the charge density over epsilon 0, and then that would be QA epsilon 0, right? The Q we just calculated. Where's the Q? Oh, Q is right here. The Q we just calculated is 8.85 microcoulomb. The A is 1 meter square. The epsilon 0 is 8.85. Let me see, where's the 8.85 times 10 to the negative 12 farad over meter, right? And then we can recalculate this a little bit. So micro, we change it to 10 to the negative 6 coulomb, 1 meter square times 8.85 times 10 to the negative 12 F over M, right? So this M and this M cancel out. So that would be, when you divide by that, actually you times 10 to the positive 12. Okay, so that would be 10 to the 6 C over F. Okay, so that is our E. Okay, again, for the units, I just want to share with you a little bit more, because as you can tell, sometimes the units is a little bit different. I will tell you what do I mean by that. It's, let's say, remember the V is equal to E times D, right? So basically it's the electrical field in the certain distance, that is going to be a V. So if E, the unit of E is C over F, and then the distance is meter, right? So you must see something like that. C, M, and Farad. Okay. And then, since the unit for V is volt, and then sometimes we use the V to represent it, and then the E can be rewritten as V over D. So you might also see the unit, which is the V over meters. Okay. And then another definition of the V is the unit, the energy per charge, right? The unit for the energy is J, which is joule, and then the unit for the Q is C, which is a charge. And then that is also the V, right? So you will also see the unit of volt. So every time I use the brackets, that means the units. Something without brackets, that's indeed the real formula. Okay. So what I try to say right here is, sometimes if you try to memorize those, it's a little bit hard, but my personal suggestion would be the following. And then you start with some fundamental. Okay. So those you have to memorize it, and then you can plug in the units and then do some derivations. And then sometimes if you find the units is different from what is being given, then you have to do some derive to try to help you, right? So for instance, the fundamental Coulomb loss is equal to K times Q1, Q2 square, and then the K actually is 1 over 4 pi epsilon 0, right? So that's your K, Q1, Q2 square. And then if we're talking about the unit for this guy right here, so 4 pi 1 is just a constant. It doesn't have any units at all. We have to look at the unit right here, which is this guy right here. So that's F over M. Right, and then these two are the Coulomb times Coulomb, and then R is the R squared. I'm sorry, R squared. That's meter times meter. And then when you flip this up, it will become M over F. So one of the M cancel out, so you will get like C squared over F M. Okay, and then, because this is a F, right? And then we know F, dot product of the distance, that gives you the energy, right? Because that's the work. Work is the equivalent like to energy. So you know this side, it is joule, and this side is the Newton times meter. So that kind of help you to understand this. Again, this is just the sum of it. There's a tons of it, right? You have to connect with the U to V, which is the energy, charge, and then potential, right? So and then the electric field connected with the potential is the distance. So with that being in mind, it will help you a little bit to figure out the different units. In particular, for something given in the problem, with the unit that's something you are not familiar with. So stuff like that can kind of help you to understand or derive that. Again, I know this is a pretty confusing, and then the only thing you can be good at this is through a lot of practice. And I wish you guys enjoy this, and I will see you next time.